All right, well, thanks for coming back, folks. I've had a fun time preparing these lectures, and hope you all have gotten something out of it. I'm glad people came to the problem session yesterday. I have posted the second problem set, and so again, there will be one more problem session next Wednesday at the same time. And so I'm going to put the link in the chat again. Just as a reminder, and you can also find the notes for today's lecture there in case you want to download those first and follow along that way. All right, as usual, just a brief recap of what we did last time on Tuesday. And so there we started with some examples of the slice filtration. We're looking at some representation suspensions of the Eilenberg-MacLane spectrum HZ. And a couple of the examples that we did, we looked at the 7 suspension of the C2 equivariant HZ, and we found the slice tower for that. We found it had an 8 slice and a 7 slice. And another example we did was the lambda suspension of the C4 equivariant HZ. And in this case, it turned out that the slice filtration coincided with the Postnikov filtration. We also talked about the Hill-Yarnall slice connectivity result via geometric fixed points, so via the ordinary connectivity of the geometric fixed points. And then finally, we talked about ROG grading, and in particular, we saw how this entered into the slice spectral sequence for the example of KR. Okay, and so the plan for today, for the final lecture, is we're going to start with some discussion of duality. So there's a couple of notions of duality that are relevant here and useful. And then we'll talk a bit about MUR and really more about BPR. And finally, sort of the very end, we won't spend much time on this, but just a brief mention of norms and how that enters in, and how this, is sort of beginning of the covariant invariant story, and how all this slice technology was developed and so on. Okay, so to begin with, duality, and just as motivation, I want to again put up this picture that we were looking at last time. And so this is a picture of the ROG graded Mackey functors, or the ROC2 graded Mackey functors of the Eilenberg-MacLane spectrum HZ for the group C2. So again, we looked at this picture last time, and this is, these Mackey functors, were something that I asked you to work out in the first problem set. And so there's a couple of things I want to draw your attention to on this picture. So in particular, we have these 2 lines above the 0 line. And again, just as a reminder, the grading in these pictures, the way I like to draw these is, so the vertical direction tells you how many copies of sigma you have, so how many copies of the sign representation, and the horizontal is just telling you the underlying dimension. So in particular, we see the sign Mackey functor. This is in degree sigma -1, so sigma because it's in height 1, but -1 to put it back in topological degree 0. And similarly, we see the Z dual in degree 2 sigma -2, and so that's exactly what I've written here. Okay. But so we know a little bit more than just the computation of this Mackey functor, because again, if we focus on this height 2 line, there are no other Mackey functors in that row. And so in particular, if we look at the 2 -2 sigma suspension of HZ, then the only Mackey functor we get there is the Z dual. And so this spectrum is an Eilenberg-MacLane spectrum because it only has a single non-trivial Mackey functor. And so it's this Eilenberg-MacLane spectrum. Okay. So again, that's this corresponding to the fact that this line only has the 1 Mackey functor on it. And of course, another way to write this same equivalence is just to suspend it or desuspend everything by 2. And so we learn that the -2 sigma suspension of HZ is just -2 of Z dual. Okay, these are just different ways to say the same thing. So again, when I think about this picture, this equivalence, I have this picture in mind, and I'm just sort of when I desuspend by 2 sigma, I'm just shifting everything down to the left. Okay, and so then I see this Z dual showing up in this spot. Okay, and so of course from this, then this tells us about the, if we like the ROG graded homotopy of Z dual because it's just, we just shifted things around, and so there's just a shifting isomorphism there. Okay. But again, the thing that we're going to focus on and what's leading to this idea of duality is that there's an apparent kind of symmetry in this picture, right? I mean, we have this kind of this cone-like situation down here, and there's another one. We're seeing the sort of the beginnings or the tips of two cones, okay, and that they do sort of continue in that direction. And so again, if we look at that height 1 spot, it looks like that's a kind of a point of symmetry. And so that's exactly what this duality that we're talking about is related to. And so let me first begin with just a discussion of how this works non-equivariantly. So again, there are two notions of duality that are relevant. There's Anderson and Brown-Kamenetz duality. And so what's the story behind these? So first, you can define a spectrum using Brown representability. It's denoted I sub Q mod Z. And basically, the point is that if you look at this formula here, because Q mod Z is an injective module, then this defines a cohomology theory. And so then this thing is just defined as a representing spectrum. And so then we get a formula like this. Similarly, we can do the same thing with Q because that's also injective. And then, we just introduce the notation IQ for this, for the Eilenberg-MacLane spectrum, the rational one. We get a similar formula. And then, from the map from Q to Q mod Z, then you get a map of spectra. And then we use that map of spectra and we define the IZ as the fiber of that. Okay. And so with those preliminaries or that notation, then we define these various duals by just mapping our spectrum X into these various I spectra. Okay, so if you map into this Q mod Z one, this is known as the Brown-Kamenetz dual of the spectrum X. This middle one is just sort of the rational cohomology, but then this one is known as the Anderson dual. Okay, so we have these three different, or really the two different types of duality that we want to focus on. Okay, and so I'm just going to mention a couple of properties to give you a feel for how they work. Okay, so let's focus on, let's say that M is an abelian group. And first of all, let's consider the case where M is a torsion abelian group. Then it's not so hard to see that in fact the Brown-Kamenetz dual of the Eilenberg-MacLane spectrum HM is just HM itself. So HM is self-dual according to the Brown-Kamenetz duality as long as M is torsion. Now another thing, of course, when we look at the rational cohomology, that's going to vanish. And then if we think about this fiber sequence that's defining the Anderson dual, then in the torsion case, we're led to the conclusion that the Anderson dual is related to the Brown-Kamenetz dual via a shift. And that's just because the rational cohomology will vanish in that case. Okay, so again, for our torsion, the Anderson dual is just the desuspension of the Brown-Kamenetz dual, which was just the original Eilenberg-MacLane spectrum itself. The other case we might be interested in is the torsion-free case. In that case, the Anderson dual behaves nicely. Namely, the Eilenberg-MacLane spectrum is self-dual in the Anderson sense. Okay. And well, you might ask, well, what if you have something that's not, not entirely torsion or free, but a combination of two, which is kind of the generic case? Well, you can just map in the torsion, and then the quotient will be a free abelian group. And then you get a sequence like this, right? I mean, so you first get a cofiber sequence of Eilenberg-MacLane spectra, and then passing to Anderson duality, you get this fiber sequence. And the Anderson dual of the free part, well, that's just the free part itself, whereas the Anderson dual of the torsion part is just the shifted copy of the torsion part. Okay, and so we get this this sequence describing at least the homotopy of the Anderson dual. We're going to get the free part in degree 0 and the torsion part in degree -1. All right. So that's the non-equivariant story. And it turns out that this also works in the equivariant world. So I think this was first investigated by Nicola Ricca. And essentially you just sort of dualize level-wise in terms of your Mackey functor. And in particular, some of the behavior that we see is that, if we look at, the constant Mackey functor Z, and then we do the Anderson dual of that Eilenberg-MacLane spectrum, well, it turns out to give us the Eilenberg-MacLane spectrum, but now for the dual Mackey functor. Okay, and so remember the dual Mackey functor, the roles of the restriction and transfer have flipped. So here, for the constant one, the restrictions are isomorphisms, and the transfers are multiplication by 2, at least in the C2 case. And then the opposite is true for the dual Mackey functor, where now the transfers are isomorphisms, and the restriction will be multiplication by 2. Okay, so that's one example. And similarly, in that sine Mackey functor, that one's going to be self-dual. I mean, here the restriction and transfer are both 0, so if you flip them around, you can't tell the difference. And on the other hand, for a torsion Mackey functor, so here's our friend G, this geometric Mackey functor, which is 0 at the top, 0 at the bottom, excuse me, and then mod 2 at the top. And that's going to be self-dual, but now in the Braun-Kamenetz sense. Okay. And so again, let's consider something where we have a mix of torsion and torsion free. So again, we have this QZ Mackey functor. Let me remind you, this looks like we have a Z sigma module at the bottom, and then a Z mod 2 at the top. And we have that non-trivial transfer map, which is the quotient. That's this Mackey functor. And so, the G Mackey functor injects in as just picking out the fixed points level. And if we quotient by that, then we just get the sine Mackey functor, which is, which has no fixed points. Okay, and so that gives rise to this short exact sequence and therefore cofiber sequence for equivariant spectra. So again, we can apply Anderson duality to this cofiber sequence, and then we get, this cofiber sequence on the Anderson duals. And again, we now know, this part is just self-Anderson dual, whereas over here we get a shift by 1. So it's a similar kind of story where we've learned that the Anderson dual of this Eilenberg-MacLane spectrum has a Z sigma in degree 0 and a G in degree -1. Okay, and if we go back to our chart, which was the motivation, we might notice, hey, that's the same thing that was appearing down here. Okay, so we were looking at the Anderson dual of this one up here, and we're getting the homotopy Mackey functors of what's down here. Similarly, the Anderson duality interchanges the Z and the Z dual, and the Z sign was self-dual. Okay, so that's exactly the duality that's describing this picture that we're seeing. So I've just described why the Mackey functors of this are the right thing to be what this is computing, namely the sigma suspension of HZ. And so I've asked you to think about on the second problem side why those are actually equivalent. Not just have the same Mackey functors, but those are equivalent spectra. All right, let me pause for questions here. So I think this is, an appealing notion of duality because it explains a lot of these phenomena that we see, and in particular, what this tells you that in some cases, let's say you want to go ahead and compute the ROG graded homology of a point, right, the coefficients of your theory, and if you just compute, half of the story, then duality will fill in the other half, and you don't have to compute those by hand using cell structures and so on. Okay, so that's all well and good. This is relevant to Berdan homology, but it's also related to the slice filtration, okay? And in particular for Braun-Kamenetz duality, so this is investigated by Ullmann in his thesis. And what he showed is that if you have some equivariant spectrum and you take the Braun-Kamenetz duality, the dual, excuse me, and then look at the, one of the slice sections of this, in fact, that's the same as just dualizing the slice section in sort of in the negative range. Okay, so there's a very nice behavior of Braun-Kamenetz duality and slices. And again, if you have something which is torsion, then Brown-Kamenetz duality is very easy to understand. Okay, so what about Anderson duality? And again, Anderson duality works a little bit better if we're working with torsion-free objects. And so, for instance, the Anderson dual of Z is going to be Z dual, and so that's something we understand. We might wonder, how does that interact with the slice story? And again, you can use Anderson duality to learn about new slice towers from ones you've already computed. Okay, so we're going to do one example together here. And so here is this example that we computed last time, the 7 suspension. This is the C2, I didn't label it, but this is in the C2 world. We found this slice tower for the 7 suspension of HZ. Okay, so now what we want to do is apply Anderson duality and see what we learn from that. Okay, so if we dualize, then okay, now we get this fiber sequence. I mean, it's directions flipped around, but I just have the Anderson dual of each piece, and so there's a sequence there. But we can understand what's going on here. We understand these pieces, namely, if I look in the middle, I mean, so the 7 suspension becomes a -7 when we take it outside of the dual, and then the Anderson dual of HZ is Z dual. Okay, so that's something that we understand. And then using our description, relating Z dual and Z, we can rewrite this as the -5 -2 sigma suspension of HZ if we like. Over here, the Anderson dual of HG, so the 4 becomes a -4 outside, and then we're using this fact that the Anderson dual of G is the D suspension of G, and so so that's why we get a -5 G in that case. And then over here again, the 1 + 3 row will become a -1 - 3 row on the outside. And again, I've used that this Z sigma is self-dual, so that's why I don't have an Anderson dual there anymore. And so this one, is a -10 slice. Number of ways to see that, but again, I like to think of it from this sort of pullback or geometric inflation perspective. That doubles the dimension. And then this one, we have a -3 row, and so that just pulls things down by 6. And so it's really just a question that the -1 suspension of this is a -1 slice. And so there we go. So there we get the slice tower for the minus suspension of Z dual, or equivalently the slice tower for the -5 -2 suspension of Z. Okay. So again, we've learned about a new slice tower starting from this one we computed. And then we can play around with this. Maybe we're particularly interested in integer suspensions of HZ. And so here we have this 2 sigma. We can get rid of that by suspending by 2 rho, which will cancel off the 2 sigmas that we have. And so if we do that, then this will become a -3 HZ. And so now we've just learned the slice tower for -3 HZ, starting from the slice tower for the 7 suspension of HZ, using this duality story. Okay, so there's some funny shifts that enter in for various reasons, but so it's, you might have expected, oh, we're going to learn about the -7 of Z from the +7. That's not quite right, but we learned about the -3 from the +7. So this is a useful technique. Any questions about these examples? And again, I didn't do an example with the Brown-Kamenetz, but again, if you're working with someone in the torsion, I mean, it just works very well because of this simple formula. So here, we've been primarily focused on the HZ, the torsion-free examples, but if you work with H Z mod 2, that constant Mackey functor, then you really just want to stick with the Brown-Kamenetz duality. Okay. All right. Yeah, I guess I'm going a bit faster than expected, actually. All right, so we may finish early today. But okay, so the next topic is the MUR and the BPR spectra. So MUR, so these are analogs or cousins, of this Atiyah's real K theory, the KR that we've been looking at, right? And so remember the idea there was, complex K theories built out of complex vector spaces, complex bundles, and so on. And if we retain the action of, C2 via complex conjugation, then we get an honest C2 spectrum from that, and that's what that's what's called KR. Well, you can do the same thing with MU, the complex cobordism spectrum. Okay, and so this was noticed by Landweber in the 60s. And so if you do that, you get a C2 spectrum that's known as MUR. Okay. And then I think it was Araki who sort of developed some of the formal group theory for this, and again saw that Quillen's idea for splitting up MU into BP, I mean the idempotent, that works out equivariantly as well. And so as long as you localize it too, then you can produce this BP or this BPR rather as an equivariant spectrum, sort of split it, and so MUR decomposes into copies of BPR. Okay. So again, this was introduced by Araki in the 70s. And then, so in terms of the computation of BPR, I think that the first written, the first published account of this is in the, widely influential paper of Hu-Krij from the late 90s, although they do say that this computation was first done by Araki but not published. Anyway, so right, so we have the ROG graded homotopy of BPR, and let me mention a couple of properties. Number one, the geometric fixed points of this spectrum is just HF2. Okay, so there's just a single homotopy group, degree 0, and they actually well get that by thinking about the geometric fixed points of MUR, which is MO, and the splitting from the idempotent. The other important property I want to mention is that if we look at the Mackey functors in multiples of the regular representation, so pi n rho for BPR when n is non-negative, then this is a constant Mackey functor. So in particular, it's determined entirely by the underlying group. Okay, so which is the ordinary homotopy of BP. Okay? And the homotopy of BP is given here. It's this polynomial algebra and these generators VI, and the degree of VI is twice, 2 to the I minus 1. Okay. So this is a classical computation, and because of this fact that these are constant, now we know the Mackey functors, or if we want just the groups in multiples of rho for BPR, and it's the same values over here, and now we have a corresponding element over here which restricts to the VI at the underlying level, and so those are just denoted the same thing but with a bar on top. So this is an equivariant class. It's in degree multiple of rho, but it restricts to the corresponding VI for BP. Okay. All right, and so one of the reasons I mentioned this fact that the geometric fixed points of this BPR is just F2. Well, that tells you that if you think about the ROG grading, right? So this is just a piece of the ROG graded homotopy, but if you think about the full thing, then as we've discussed, geometric fixed points corresponds to looking at that class A that we were talking about last time with KR, and looking at everything that's not A torsion, right? So you look for infinite A towers in the ROG graded homotopy, and that tells you about the geometric fixed points. Right? So this fact that the geometric fixed points are just in degree 0 tells you that, for instance, all of these classes that we have here, these must be A torsion for some power of A, right? So we just see that from the geometric fixed points. All right. So yeah, I guess what I want to do is just describe what the slice spectral sequence looks like in this example. Okay. And so in order to do that, of course, you need to know, well, what are the slices, right? That's the E2 page of the spectral sequence. And so this is one of the important results in the Curvaire paper of HHR. they have this result they call the slice theorem, which describes the slices of various spectra. In particular, applies to MUR and BPR. And so what they say is that, first of all, this only has slices in even degrees. And then there's a formula for what the even slices are. And they're all just row suspensions of the constant Mackey functor hz. I mean, it's localized at 2 because that's what you need to define this. But anyway, so just row suspensions of hz. And there's a precise formula for how many summands you have for each slice. So each slice is a wedge of these things. And so the number of summands just comes from those VIs. And so, just to make that clear, let's look at a couple of examples. So in particular, the 2 slice, we just have the V1 in degree row for the homotopy. And so that gives us a single copy, of the row suspension of Hz. That's the 2 slice. So it's the same 2 slice we saw for KR, okay? The same 2 slice. Actually, the same thing happens for the 4 slice, because again, if we look at the monomials, we have V1 and V1 squared. V2 hasn't shown up yet, right? That shows up in 3 row. So in 2 row, we just have V1 squared. And so again, we have the same slice that we had for KR. But then once we get to the 6th slice, okay, now V2 has shown up. So now we get 2 terms. And so therefore two copies of the 3-row suspension of Hz. That's our 6th slice, etc. Okay, so we're just looking at these monomials and just keeping track of where they show up. And then it's just an algebraic calculation of what the slices are because of this slice theorem. Okay, but again, when I emphasize in low degrees, this looks exactly like the KR that we were looking at last time. All right, so again, this is the picture that we sort of ended with last time, which was the ROG graded homotopy of KR. And again, I made this point last time that the geometric fixed points, you can see it's polynomial in U squared, and you're supposed to be able to read that off from this picture. I mean, this picture is only a partial picture, of course, but the point is that here is U squared, and it's supporting an infinite A tower. And that was, and then all the multiples also support an infinite A tower. And that's why we were seeing this polynomial algebra in U squared. Okay. And so again, how did this come about? What was happening in the spectral sequence? Well, the element U was sitting here. It's, it didn't survive after homotopy, but it was sitting there. And there was a differential coming off of it, truncating this A tower on the class V1, which sits here. So that was our D3 differential that we talked about last time. So we had a differential on U, truncating. So here you see this truncated A tower. And here's all the multiples of V1, which have their A towers. Okay. And so the same thing is going to happen in BPR. We're going to have U truncating this A tower on V1. Okay. But now we also have the higher VNs. So V2 will show up here. It shares a degree with the V1 cubed. And so that there'll be that A tower to contend with, and that'll be the role of U squared to truncate that A tower, okay, etc. Okay, so that's sort of a bird's eye view of what happens. And so let's just sort of look at what that looks like, in terms of the kind of pictures that we were drawing last time. Just any quick questions on this picture before we look at those? Okay, so again, this is essentially the picture that we were looking at last time. This is the E3 page. This is the integer graded part of the E3 page. And we saw this differential here, right, from U V1 squared. I guess I forgot to put the bars here, but from U V1 squared to A cubed on V1 cubed. And so that was this differential. We kind of saw that differential back on the first lecture. But now we have another class sitting here, right, which is the V2 as well, right? So along this 3th slice, we see the V2 copies as well, right? There's a V2 squared up here, etc. Okay, so when we do that differential, this class will survive. Okay, but again, when we look at this, V1 squared is a permanent cycle. And so this really corresponds to a differential on U, as we discussed last time. And so to see that, you have to go to the -2 sigma part of the spectral sequence. And so here's that picture. Again, this is the picture that we were looking at last time. So there was U truncating. So it's hitting A cubed on V1. Okay, so basically the same picture, except now, again, on the 3 slice, we have 2 dots everywhere because there's 2 copies, right? And there's a piece of the 6th slice, etc. Okay. And so again, once we do this differential, there will be some classes left over. I mean, A cubed V2 will survive, etc. And then, oh, I think I lost one of my slides here. Oh, that's unfortunate. I did have a slide that was showing the D7 differential. I'm not quite sure what happened to that. Well, that's unfortunate. Okay, so if you then go to the -4 sigma page, I'll put that slide back in on the lecture notes. I'm not sure what happened to it. Again, what you'll see, that's where U squared will live. And what you'll see is this formula that I've written here, but for some reason the picture has disappeared. And so there's a formula, so that U squared will support the differential that I was indicating before or suggesting before. And it's going to be now the 7, the A to the 7th power of V2. But so again, it's truncating the A tower on V2. And so HHR produces family of differentials. And so here's the first 4. And if you like, here's the general formula, although to me, like parsing a general formula like that is, takes significant work, and I much prefer the examples. Okay, and so anyway, so this is the pattern of differentials that truncates all the A towers that need to be truncated in this example. Okay, and so then, we're left to think about, well, what survives a spectral sequence? And this is not an exhaustive list by any means, but well, certainly A to the K, all the powers of A survived, right? And those were meant to survive because the geometric fixed points did have something in degree 0, right? It has Z mod 2, and that's this A tower, of 2 torsion is supposed to survive. And then, the various powers of A supported differentials. But U was not torsion, right? It was torsion free. And so then 2 times those powers of U will survive. And that's what led to those Z duals before. But this will not support any A multiplications. We also have the various classes Vn or Vn bar. Of course, we knew those had to be there because that's sort of, that was the starting point which led to the slices. We had those classes Vn. But all of those have been truncated, right? So V1 is A cubed torsion, V2 is A to the 7th torsion, etc. But then there are some other classes that survive as well. And so, for instance, U squared of V1, why does that survive? Well, this is a class that that wanted to support a differential, a D7 differential that would have hit A to the 7 V1, V2. But this class was already killed on the E3 page, right? Because there was a D3 differential that was hitting A cubed V1. So this has already been killed off. And so then this ends up surviving the spectral sequence. And similarly, U to the 4th V2, etc. Okay. All right, so we get a bunch of classes like that survive as well. Okay, so that's kind of a description of what goes on in the spectral sequence here. All right, and so then the last part of the talk will be discussion of norms and how that enters into the story. Because any questions about the spectral sequence before we go to the last section here?
Were these slice differentials completely determined by knowing the geometric fixed points of BPR?
Yeah, I think in this case you can. That's right. Mm-hmm.
Okay.
Bert, I want to make a comment.
Yeah.
That class U squared V1 bar can be thought of as a Toda bracket or Massey product, whichever you prefer, in which V1, let's see, A7th A to the 7th V1 bar, V2 bar is 0 for 2 different reasons, and that leads you to a Massey product. And similarly with those others. And I think you get maybe higher, maybe more complicated Massey products involving powers of U times products of V's, maybe something like that.
Yeah, thanks for that comment, Doug. So yeah, I mean, this is sort of typical in this business that I mean, you can get these Massey product descriptions of classes, which turns out to have wide consequences. It's very useful. Thanks for that comment. All right, so again, the last part of the lecture here, I just a small discussion of norms. So what's the idea behind this? In the first lecture, we did that setup. We were talking about various constructions that exist in the world of equivariant stable homotopy theory. In particular, we discussed induction, which is a way to go from H spectra to G spectra, or at a simpler level, it's a way to go from H or based H spaces to based G spaces, or even at the unbased world. So the formula was just we're starting something with an H action, and we're inducing it up, so smashing over H with G. And if you think about what this looks like at the underlying level, it's going to look like a wedge of copies of X where you're indexing over the orbits of H and G. Okay, and so we already had an H action on X, and now G is going to permute the various orbits, but then we have to remember the H action on X. Okay, and so this leads you to I mean, yeah, this is one way to think about the induction. Okay, and we think of this as kind of an additive process because we're sort of adding or taking wedges of copies of X. But then one thing you can notice is that, well, another thing you could do is instead of adding, is you could multiply, but use basically the same formula. Okay, and that works. That gives rise to what's called the norm. So it works this way at the space level, but again, you can define this at the spectrum level. So this was first defined by Greenlease and May in the 90s, and then really made heavy use of by Hill, Hopkins, and Ravenel, again, in their Curvaire work. Okay, and so this is a way of taking a spectrum or space for a small subgroup and producing one for a larger group. And so in particular, this is important in the cases of MU and BP. So these are spectra that are defined using geometry for the group C2, but there isn't an obvious way to produce such a spectrum for larger groups. And so one thing you can do is norm up MUR or BPR to one of these larger groups G. Okay, and so this is the notation that HHR use for this norm. They just put the double parentheses G. Anyway, so that's just notation, but so we're just taking the norm from C2 to G. So in particular, if G is a cyclic group of order 4, then the norm from C2 to C4 is just taking 2 copies of whatever your spectrum are, but now inducing it with a certain C4 action, right? So in particular, if we're looking at BP, we're norming it up from C2 to C4, then the underlying homotopy is going to be, the homotopy of BP smash BP. In other words, this is BP star BP, which is a thing of interest for sure, right? Okay, but again, now we have some equivariant action on it. And so again, this plays an important role in the Curvaire story. The slice theorem does apply to these normed spectra as well. So what you get as a consequence of the slice theorem is that the slices of the norm here, they're all even, and they're all of this particular simple form. So you have these induced representation spheres smashed with the constant Mackey functor HZ. Okay. So we did some examples of slice tires, which looked very different from this. You have various Mackey functors showing up that are not just constant Z. But in this case, you do get these very nice slices, these very simple slices. Okay. All right, and so just sort of a quick discussion of sort of then what's the story for HHR coming from this? So they produce this normed up spectrum, and for them, the norming up from C2 to C8 turns out to be the right thing to do. They produce a class which turns out to be in the 19-row homotopy of this normed spectrum, and then they invert that. And this is an equivariant spectrum, which sort of is the key player in the Crevert story. So using, the slice technique was involved and developed in order really to understand this MUR, and they were able to show using that there's sort of a gap in the homotopy, and then when you periodize it, when you invert this element D, then that gap propagates. And the point was that there are these classes, these Crevert classes in homotopy, in the homotopy of spheres that that we'd like to understand whether they exist or not. And so what HHR did was show that if they existed, then they would be detected in the homotopy of this spectrum. Again, because of this gap, this is a very small gap. It's a gap between -1, -2, -3 homotopy vanish, which is pretty small. But then you again periodize it, and then that gives you these small gaps later on in the higher homotopy groups. And the point is that those small gaps are exactly where these Crevert classes would appear. Anyway, so that's the sort of the main idea of the Crevert article, which show that these higher Crevert classes do not exist. Unfortunately, the periodicity is just high enough that we have this class in degree 126 that's we still don't know about, but nevertheless, this is a tremendous breakthrough. Yeah, I guess like I said, I think we're going to finish a little bit early today, and so yeah, that's what I had to say.